What is model-based RL? Well, we want to maximize the reward, but we want to do it by building a surrogate model of the world. And so instead of trying to optimize under the true model of the world P through trial and error, right? We're going to model, we're going to go from P to some model P hat. We're going to pretend that the model P hat was the true model of the world, and then try to find the optimal actions under our surrogate model P hat. So that's model-based RL. Cool. So the general template of a model-based RL algorithm looks something like this. You start by collecting some data, use it to learn a model. Model is typically learned with supervised learning. Then you use it for planning. Planning is making decisions on a particular instance, right? You decide to play actions using your planner. You then collect more data, update your model, and repeat, right? So it's important that in the difference between policy learning often is that in policy learning, you just learn a policy pipe, and then at test time, you just do feed-forward inference, right? In many model-based RL algorithms, you do decision-making at test time. So at test time, you don't just do feed-forward inference, you do some amount of what you'd call planning or decision-making or optimization at test time. Okay, so the most naive algorithm we did was we said we're going to collect some data. We're then going to learn a model with supervised learning. So one-step supervised learning, which is maximum likelihood. We're then going to do planning with the variant of random shooting plus model predictive control. As a model predictive control means we're going to run the open loop for some steps and then replan, right? And then we're going to repeat. Okay, so what is the issue with this type of model-based RL method? Like, why wasn't it enough? You remember? Like, we're gonna sample random actions, then we're gonna choose the best actions, we're gonna play the first one, then we're gonna sample random actions again. Right? Why is that not good enough? Yeah. Compounding error is one thing, yeah. The MPC should help with compounding error a little bit, but it's certainly still a problem. You're not being greedy because you're considering you're choosing the best sequence of actions, not the best action. You're saying the best sequence of action, then play the first from that best sequence. That's not actually greedy here. Other thoughts? Yeah. Generalizability. What do you mean by that? So one issue here is that if your action space is pretty high dimensional, then you're sampling IID in this larger action space, and you're hoping you're going to find something that has signal, right? So like if I have a humanoid robot, I'm like sampling random stuff and hoping the humanoid robot will walk. And so you're searching for a needle in a haystack, which can be quite challenging for high dimensional action spaces, right? But it's still better than open loop planning. So here, the swimmer. The next thing we did is we said, okay, the problem is you have needle in a haystack problem, which is high variance. And so we're going to go to a variant called MPPI. And what MPPI does is it says that rather than just sampling IID, you're going to reweight the samples according to the exponentiated reward, right? And so you're going to say that I'm going to focus my sampling on the regions that are getting rewards. I'm not going to waste samples in places that don't have reward, right? So I'm not going to sample IID. So I'm going to follow this procedure where I sample, then I reweight things according to the exponential reward. And I sample more the next time near things that have high reward. And so I repeat this procedure k times. I sample a bunch of stuff. I increase the likelihood of stuff that got high reward, and then repeat until I'm convergent, and then I play the action. Right? Yeah.
So when you do this application, is it now unbiased? It's unbiased, but before you have all the options, and now you're only choosing one, so to speak.
Is it biased? So I wouldn't think of it as biased. I think you're just sampling from a different proposal distribution. So it's kind of like importance sampling, but you're changing the importance sampling distribution. So it still remains unbiased. It's just lower variance. In the same way that importance sampling is lower variance. Okay, so you run this k times. Remember this procedure here. This iterative procedure happens within every step of decision making. So every time you're acting in the world, let's say I'm at some state S here, I'm going to do this MPPI procedure k times. I'm going to get an action to play. I'm going to play it, and then I'm going to repeat MPPI. Right, so MPPI happens within every step of decision making, which makes it kind of slow. Right, so if you want to do it for any big model, so the reason you don't do MPPI on like huge video prediction models is because it can be kind of slow. And remember, every time I'm doing this, I have to like run forward through the model. I have to score things with my reward model. I have to reweight, I have to sample, I have to do this k times, right? So the number of forward passes through your model is quite large. Okay. All right. So someone asked last time, like, is an MPPI kind of obvious, right? And so I think it might be useful to think about how we get to MPPI from first principles. So let's start by like thinking about some nominal action trajectory. Let's call it U, right? What we're going to do is try to derive how we get to MPPI. So we start with some nominal trajectory. Let's say you add some disturbances to that nominal trajectory. So you have U 0 to H minus 1. Let's say you added some noise epsilon to this trajectory. What you want to do is measure the cost. Cost is just negative reward here. So you want to measure the cost of this disturbed trajectory. And so you want to say the cost is the sum of costs over different time steps when you take actions which are ut plus epsilon, right? And the goal in MPPI is to say, how do we choose the disturbance as epsilon so that we find something that minimizes the cost while not deviating too far from my current sampler? Right, so my current sampler is like, if it's an iterative process, I have like my sampling distribution now, call that P, right? What I want to do is I want to find a distribution from which to sample the disturbances such that I minimize the cost while not deviating too far from my base distribution of disturbances, right? So this P will update iteratively, but the point here is that you want to like, it's KL constrained optimization, right? You want to find something that minimizes cost while staying pretty close to a base distribution P. Okay, so what we'll show is that the solution to MPPI is basically the same thing as the solution to this optimization problem. Yeah. Okay, so what you can do is you can write this optimization problem as a constrained optimization problem. The constraint is that Q needs to be a valid probability distribution. It means it needs to integrate to 1, right? And so remember, you want to minimize the expected cost plus the KL divergence between Q and P. And so you construct a Lagrangian. You add a Lagrange multiplier eta. And then you take the gradient and set it to 0. Okay. So we're going to skip through the like actual taking of the gradient. When you take the gradient, this kind of thing, you get essentially this. It's pretty easy to compute. Like this term, the gradient with this, you can take the gradient of this thing with respect to Q, right? So this thing becomes S of U plus epsilon. This thing, you just use the product rule. And this thing again is just like, this thing is becomes 1. So you can simplify the gradient to be something like this, right? And then you rearrange these terms. You just move this to the other side, move this to the other side, exponentiate, etc., right? And what you can work out is that you can show that Q star epsilon is proportional to P of epsilon times the exponentiated negative cost. Okay. And so you can show that basically the updated sampling distribution that minimizes the cost while not straying too far is just like the reweighted previous sampling distribution by the exponential negative cost. And so this is just how you can derive MPPI. So the paper does like a very complicated job of doing this same thing. Cool. Does that make sense overall? This is also the same math you use for advantage weighted regression and RWR and reps, and a lot of different algorithms in the literature have the same. It's just like you set a trust region and you like find the optimum thing in the trust region. Yeah. Sorry? The trust region is the KL divergence. So you don't want it to deviate. When I say trust region, I just mean you want to say that like it doesn't deviate too far from the Okay. So that was MPPI. Any questions? How do we feel about MPPI? So here's a pop quiz. What problem should we use MPPI on and what should we not? Like those of you who've used MPPI, where does it work well? Where does it not? Share knowledge with the class. Yes. Low dimension problems, yeah. So in those cases, is there a reason to use anything else? Are there any cons? Does it like exploit things? Is it slow? Like what's the behavior you've seen? Nice. Yeah, if you have simple model and you replan, you can get away with a lot. Any other thoughts about NPPI before we move on? Okay. All right. So the next thing, I think someone said compounding error, right? So the next thing we're going to think about is compounding error in dynamics model. So one thing you'll notice here is that we are like overall template, right? It looks a lot like imitation learning. Like we took the sequential decision-making problem and we treat it like a non-sequential decision-making problem. We treat it like a one-step problem, right? And then we're going to say, hey, we're going to roll out things under this model, but we trained it to be one step, and then we're going to roll it out to be multi-step, right? And same thing in imitation learning. We trained it to minimize the one-step error, and then we rolled it out multi-step in the environment. So essentially, you have the same compounding error problem that you have in imitation learning. You have it in model-based RL. And essentially, the issue is that your learned model is a one-step model, and your rollouts are multi-step rollouts, right? And so remember in imitation learning, is your nominal path, you made a mistake, you make a bigger mistake, a bigger mistake, a bigger mistake, right? In this case, in your model, let's say the true model was supposed to predict this, you predicted something a little bit off. You can make a bigger mistake, bigger mistake, bigger mistake if you're going more and more out of distribution. So the way this will like manifest in, like, for instance, models where your input is images, the images will get more and more and more blurry. So often you'll see like video prediction models will have blurriness after 10 frames or 15 frames. It's often called model bias, compounding error, just a name. But it manifests in almost the same way as imitation learning. So if I had data coverage over everything, this probably wouldn't happen. But it happens when I like go to some out of distribution next states and I start hallucinating things.
In image models, can we do anything similar to the diagram where you can, like use real life to correct the prediction?
Yeah. So you can either collect more data and correct for it, or what a lot of diffusion models do is they like inject noise and they like fix things which are noisy, and that kind of like serves as like self-correct. So there's this nice paper called diffusion forcing, which tries to inject noise at different levels so that you're always like denoising at future states. And that leads to much less blurry predictions over long runs. Okay, so essentially the process is the same as in imitation learning. You make a little mistake, you go to out of distribution next state. That leads to a worse prediction in the future. Worse, 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 worse. Okay, so that results in like many models only being able to roll out for 5 to 10 steps. Now you can like plan on those 5 to 10 steps and then replan, but you can often be greedy. Doesn't always work that way. So the first idea is to say, well, why are we training on a one-step objective? What if we train on a multi-step objective? So what we're doing typically in model-based RL is we're training on a one-step objective, which is maximize likelihood of S prime given S8. What you can do is you can do the multi-step objective, which is saying, don't just maximize the likelihood of one step, like do autoregressive generation and maximize the likelihood of multiple steps, right? So you can say, let's say you start at some state S, got some action A, you'll roll out S prime hat, right? And then from S prime hat, you'll feed in A prime, you'll predict S hat double prime, and you'll try to match the loss at like multiple different steps when you're rolling out under your own predictions. So it's like not opposite of teacher forcing, right? So you're saying that like, I'm going to roll out under my own predictions and I'm going to predict the loss at multiple steps. And I'm going to maximize the likelihood across multiple steps rather than just at one step, right? So I want it to be good under its own predictions for multiple steps. And so in some sense, what this is doing is it's like removing the mismatch between train and test. And I'm saying that I'm just going to train under the same distribution I'm going to see a test. Yeah. And so the nice part here is that you like don't have the same compounding errors because you trained to remove them. The challenging part is that this is like super hard to optimize typically. And so the thing on the left is often called equation error. Thing on the right is called simulation error. But you can kind of think of it as like you've created a computation graph where you start with like S, you run through the model, and A to predict S hat prime. And then you like run through the model again to predict S hat prime prime, etc. And then you have loss at all of these, and theta goes through each step, right? Kind of like an RNN. And empirically, what folks find is that this is like often super hard to optimize well. It's a non-convex objective. It's quite hard to get the loss to go pretty low. And so it just doesn't seem to work that well in practice, even though it's probably the right thing to do. And so the trade-off here is that it's the right thing to do, but the optimization is way harder. And with gradient descent, you don't seem to find the right solution. So we resort to other things. Okay, so we're going to have compounding error, but we don't want the compounding error to fuck up our planning, right? So how might we deal with compounding error in model-based data? And so the issue, the second idea that folks had was to say, okay, if I'm going to be hallucinating things, if I'm going to go OOD, if I can measure when I've gone OOD, then I can account for it and say like, this is no good. You're predicting something that doesn't really exist, right? And so if I can estimate my uncertainty and account for it in my planning procedure, then I'm not going to hallucinate as much. The problem with hallucination is like, for instance, I can think that this action will take me to success even though it won't, and I'll play the wrong action, right? So if I can account for something being uncertain, then I can like be conservative under that estimate. And so typically when you have a maximum likelihood model, your true is in solid, your rollout is in dotted, but you can't really tell that this thing is uncertain. What you want is to be able to tell that, hey, like as I'm going more and more out of distribution, I'm getting more and more uncertain. And if I can tell that I'm more and more uncertain, then I can penalize that in planning. And I can say that I don't want to deal with rollouts that are uncertain. I just want to be able to plan under where I'm certain. Right? And so this is the first instance of a general idea of pessimism. We've talked about pessimism in Q-learning a little bit, but if I'm able to estimate my uncertainty and penalize it, then I will never, or I will try not to, take actions out here because I just am not certain about them. Now, the trade-off is that these things might actually be good. We just don't know that they are, right? And so the idea here is if we can estimate our own uncertainty, then we penalize for it. And we change the planner, even though the model is still hallucinating. We just make sure the planning doesn't exploit it. Okay, so what is uncertainty? Right? Uncertainty is like an overloaded word. What does it mean? So I think typically there's two types of uncertainty. There's aleatoric uncertainty, which is stochasticity that is inherent to the environment. And there's epistemic uncertainty, which is stochasticity that's part of the model, right? So there's something like your car is moving and there's some noise in the like steering wheel, right? Like that is aleatoric uncertainty. You can't control it, right? Whereas epistemic uncertainty is like, well, I haven't driven enough cars, and so I don't know exactly how it works, right? So epistemic uncertainty stems from the lack of data, comes from the model. Aleatoric uncertainty comes from the environment. So here's an easy way to think about it. Like imagine that you had these data points, which are shown in green. The green X's are your data points, right? Aleatoric uncertainty is like the width of these data points. You can see that at any point, it's not like a single point. It's like there's things on the y-axis. At the same x, there's many different y's, and that spread is aleatoric uncertainty. And now in something where you don't have enough data, right, the number of models that you can fit is high, right? So like a number of models can fit both this point and be unexplained in places where you don't have data, right? And so in those places where you don't have data, you have epistemic uncertainty. So essentially you can say that if I look at all the models that are consistent with this data and this data, right? There's an infinite set of models, but the variance between those models is what characterizes your epistemic uncertainty. If I had more data in these regions in between, I could like cut out those hypotheses to just the hypotheses I care about, right? So epistemic uncertainty stems from the lack of data. Aleatoric uncertainty is irreducible uncertainty in the environment. Yeah. Okay. So how does this work? Well, aleatoric uncertainty, if I have a probabilistic model, let's say I had like a diffusion model or a mixture of Gaussians or something, I could estimate a probability over these things. Epistemic uncertainty is harder to measure. So let's think about epistemic uncertainty, but that's the one we care about, right? It's like when you have model hallucination, it's not because your model is multimodal, it's more because you just haven't seen enough data in places where you haven't been. And so what we're going to try and think about is how do we measure epistemic uncertainty? Epistemic uncertainty being uncertainty because of lack of data. So the goal of most methods for measuring epistemic uncertainty is to measure this posterior. So if your parameters are theta and your data is d, right? So your data is d, let's say S, A, S prime, and the parameters of your model are theta. What you want to get is a posterior, which is P of theta given a data set of S, A, S prime, right? What is the distribution over models that are consistent with your data? So for instance, like in the previous example, like you'll have a small set of models that are, you'll have a set of models that are consistent with this and this, but will have some variance, right? And so if I'm able to measure this P of theta given D, I can measure like, okay, in this region, I have a high variance. In this region, I have a high variance, which means that I should like not trust those things much more, right? And so if I'm able to measure P of theta given D, then I can penalize my planning from hallucinating and being overly optimistic. So our goal with epistemic uncertainty is typically to estimate P of theta given D. So this is often called your Bayesian posterior over weights. And the challenge is that it's hard to estimate directly. So given, let's say I had, sorry, let's say I had a model, P theta of S prime given SA, right? This gives me likelihood, right? And let's say I had, or maybe an easier way to write this is P of S prime given SA theta. Let's say I had a prior over models P of theta, there's a prior over all possible models. What I'm looking for is the posterior, which is P of theta given SA S prime. Yeah. So the posterior is like, it's just like in any Bayes rule, right? You have P of X, P of Y given X, and you're looking for P of X given Y. In this case, you have the likelihood, the prior, and you're trying to get the posterior. Okay, so why is this hard to compute? Why is it hard to compute the posterior? What makes it hard to compute the posterior? Yeah.
We need to integrate over
Integrate.
different disk.
Yeah. So we have to integrate over the parameter space, right? So essentially to get the posterior, you have to do this divided by this. This thing is an integral of P of D given theta, P of theta, D theta. So if it's a neural network parameter space, you have to integrate over the entire space of parameters. I don't know how to do that. So there's lots of ways to approximate posteriors. I'm not going to cover all of them. But generally, the challenge in posterior estimation is when you have the Bayes rule in a continuous space, you have to integrate over all the parameters, and that's going to be a huge pain. So there's lots of ways to deal with this. The first is Bayesian neural networks, right, which try to estimate a probability distribution over parameters using approximations to they use approximations to P of theta given D using like simpler families of probability. We'll talk more about ensembles, which are easier and more scalable. But in general, what these try to do is they try to model some distribution over parameters. If I can model a distribution over parameters, I can measure uncertainty and I can penalize planning. That's the basic idea. Okay, so the first type of method, it's called Bayes by backprop, but it's basically using this idea of variational inference. How many folks are familiar with variational inference? No? Oh, good. Okay. Well, the idea of variational inference is that if I have a pretty hard to compute posterior, if I know likelihood, if I know the prior, but I have a hard to compute posterior, what you do is you try to introduce a simpler posterior family Q, and then you try to minimize the divergence between the simpler posterior family and the expressive posterior family, right? And so this is the idea behind diffusion models, behind variational autoencoders. And essentially, it's saying that when I have a complicated posterior, I approximate it by a simpler posterior. So in this case, for instance, our posterior might be like independent Gaussians for every single weight and bias, right? So it's going to be our simpler family, which we know how to sample from, is independent Gaussians for every weight and bias. And we're going to try and find the member of this class, which is closest to this thing. And the trick behind variational inference is when you want to minimize this thing, the denominator disappears. And so to find, you don't have to like compute the posterior to find the thing that is closest to the posterior. And so we'll cover variational inference in more detail in the next class. But one way of doing this is that you can try and find a simpler family Q of theta given D and optimize it with variational inference. The challenge here is that Q of theta given D often becomes overly simple. Like you have to measure these like your uncertainty is like independent Gaussians over weights and biases, which doesn't represent real uncertainty. So a big challenge in Bayesian neural networks is how do you represent something which is tractable to do variational inference over, but is still expressive enough to capture uncertainty that you care. The thing that people use more so is the idea of an ensemble. And so an ensemble is basically saying, rather than training one model, let's train k different models, right? So we train k different models. And you can show that this is like a crude approximation to your posterior. And so the way to think about this is you train k different models independently. And in regions where you have lots and lots of data, right, because the models are all trained on the same data, they will agree on these things. But for places where they're not trained, right, each model will start with a different initialization, will have different optimization. And so you can have them being quite separate, right? And so in regions where they're similar, the variance is small. In regions where there's not a lot of data, the variance is large. So the key idea behind ensembles is just you train them on the same data, and the variance between different ensemble elements leads to an approximation of your epistemic uncertainty. And so if you have lots of data, all your ensemble elements would agree. If you don't have lots of data, your ensemble elements often disagree. Okay, so what's the challenge? Like, why might this not work? Or when might this not work? So intuitively, this makes sense, right? More data will show up more times in the training data. All the models will be consistent with it. But when is it a bad approximation to your uncertainty? Yeah.
All the models have the same architecture, they might have similar specified.
That's right. That's right. So often, it's not super well understood when this inductive bias shows up. Like often you don't even train them on, like the only thing you separate between them is initialization. And so often they do collapse to the same thing. And there's like newer methods which try to make the ensemble elements disagree more and so on. And that kind of helps. But still an open area of research, I'd say. Okay, but what have we done? We've tried to estimate our an approximation to our epistemic uncertainty. And so with ensembles, you can think of it as like I'm training k models for predicting P of S prime given SA, right? And then given those k models, I see how much they disagree. And if they disagree a lot, that probably means I'm out of distribution. I shouldn't trust my planner, right? And so going back to model-based RL, what does this mean for model-based RL? What this means for model-based RL, I'm going to learn k different models with the same maximum likelihood objective, but they're initialized differently. Maybe they're trained on independent subsets of the data, right? But they end up agreeing on things where you have lots of data and disagreeing on things that you don't have lots of data. Then you say, given these ensembles, I'm going to rework my planning procedure to be uncertainty aware. And so I'm going to say, instead of doing something with a single dynamics model where I'm going to like pretend that it's the true world, I'm going to do it under my ensemble of dynamics, right? So in things where I know what's happening, the uncertainty is small. And things where I don't know what's happening, the uncertainty is large, right? So there's two ways that folks have tried to do this. The first way is to just say, let me take the expected value under this ensemble of dynamics. So what I'm going to do is every step, I'm going to sample something. I'm going to sample something from a different element of this ensemble. And so I'm going to take one step with one element of the ensemble, then another with another element, another with another element. And those things only agree on things where your uncertainty is low, right? So it's unlikely you're going to find an action sequence that's going to be low reward and it's good across all of these various ensembles unless it's in the low uncertainty region, right? So the idea is like if all the models are disagreeing, it's unlikely that you'll have something in this path that is good for all the models. And so the first idea is to say, rather than optimizing something under a single model, optimize something in expectation under an ensemble of models. And so that penalizes some uncertainty. The more direct way of doing this, which I find a little more palatable, is to just say, if I can measure uncertainty, then why don't I just penalize uncertainty? And so if I can measure uncertainty, let's say I've measured uncertainty by looking at the variance in my ensemble, then why don't I just penalize uncertainty? And so you can kind of think of this as you're constructing a pessimistic MDP, where you're saying that anytime there's epistemic uncertainty, I just penalize it, and I never plan for anything where I'm uncertain. Right? And so I will like basically say, in these cases, my epistemic uncertainty was large, and so I get a large negative penalty in my cost. And so I'll never pick these things because they're uncertain. And so a lot of the methods for offline model-based RL and even online model-based RL basically penalize for high uncertainty regions, and that's what you call pessimism. Yeah. You speak up. Because in this case, we're assuming that the reward model is known. So the only thing that is in your planner is your model, right? Like there's nothing else that is learned in this process. And so that's the only thing to have uncertainty over. Yeah.
Can we only do this with an ensemble? Can we manually only do this, or can we do it without?
As long as you have a way to measure your uncertainty, right? So if I can, if I can replace that with any measure of uncertainty, then so if we first if you had a Bayesian neural net, right, and you could measure uncertainty for that Bayesian neural net by like you don't need an ensemble, but if you had like a posterior estimate directly and you looked at the variance or the entropy of that posterior ensemble, I think you could also do that.
But it's typically done.
It's the easiest way to do it that I. Cool. All right. So the idea here is that if you're going OOD, measure your uncertainty, penalize that uncertainty, and then plan under your pessimistic cost function. And so you're never going to go and reward things that are hallucinating success, but are highly uncertain. Okay? Yep.
This will never find like any kind of like revelation and
Yeah. Yeah. Right. That's right. So the challenge with this kind of method is that if I'm gonna like, am I gonna like invent scientific things with this? Probably not, right? And so the interesting thing, if you're thinking about RL for scientific discovery, is you wanna be optimistic, but you don't want to hallucinate. And so how do you stay optimistic while not being? The open question. The way I would do it is like, what you'd want to do is you'd want to stay within things that you know, but new combinations of things that you already know. And so what we'd want is like maybe the trajectory is out of distribution, but the transitions are all in distribution. That's how I would do it. But I don't know the answer, I think. Okay, so does this work? So actually the results that Anushka showed earlier with the Bowding ball doing things did MPPI and it did uncertainty penalized models. And it's also useful across a bunch of other tasks, which back in 2017 were pretty cool. So yeah, that's the idea of uncertainty-driven models. There's other ways you can deal with it, and here's one that I think is kind of fun, which is a third idea, which is to basically use some of the insights that we had from imitation learning to make model-based RL better too. And so there's a paper called Data as Demonstrator from some folks at CMU. But basically, it's going to use the same idea as Dagger, right? So it's going to say that like, imagine you had, this is the sequence you wanted to follow. When you sampled from your model, you reached these things which are OOD. What you're going to do is you're just going to create corrective labels. And so you're going to create corrective labels that say, okay, if you're at X1 hat, synthetically go back to X2. If you're at X2 hat, synthetically go back to X3, and so on, right? So you generate on-policy rollouts from your model, and then you synthetically create labels that go back from X1 hat to X2, X2 hat to X3, and so on. And so you're like essentially using the same idea as Dagger, but in model-based stuff. Where does this start to get tricky? So the important thing is like, we're using the next time step as the target for X1 hat. So X1 hat goes to X2, X2 hat goes to X3, so on, right? So where does this start getting a little tricky? Like why might this not? Let's think of a pathological failure case, right? So where is this going to be a problem? So imagine that you like showed up here and you told me to go here. Like, when is that going to be a problem? Yeah.
you like can't like you're like crossing a bridge. You have to
Right.
fall off.
You're hallucinating a path that doesn't exist. Or imagine that you had like two different trajectories and you like were over here, you're telling it to go, okay, maybe this is not drastic enough, but imagine that there was a second trajectory that was like way further away or something. Eh? And so your hallucinated path is over here. Really what I want to do is go to this thing. But because I'm just going to the next time step, I'm going to here. So you can have these like conflicting labels, and just going to the next time step is not always the right thing to do. So not that many people end up using this kind of method in practice, but I think it's a good idea that we should revisit 2026. Okay, so that is uncertainty-based models. Any questions with that before we keep going? Let's say you're dealing with model hallucination, which is coming from the fact that you've trained one-step models. You want to deal with that by measuring uncertainty and penalizing it. Good. Okay, so if we have this thing, is this model? Are we done with model-based RL? Is it solved? Right. So one of the challenges here is that this is pretty slow, right? Especially if you're doing something like MPPI, I'm like running it in real time. I'm running k iterations. Each time I'm sampling through the model is big, and the reward model might also be big. And so I'm like running this extremely slow process at test time. Okay? And so like if I'm running, let's say a humanoid really, really fast, or like a drone extremely fast, can I run MPPI super fast? Maybe, but not with a big enough model, right? So one solution is to make your model smaller. But the other solution is to say, let's amortize planning, test time planning, into training time policies, right? So it's saying that like, let's use ideas from imitation learning, et cetera, to say, instead of having a slow policy or slow planner that you compute at test time, let's instead amortize that into a policy at training time. And then at test time, you just do feed-forward inference, right? So the same thing we've done earlier. In Q learning and in policy gradient, we just run a policy at test time. But the way we're going to synthesize the policy is through model-based RL, right? So we're going to use the model in order to synthesize the policy. Right? So the 2026 buzzword for this is RL in a world model, but it's like an idea from like the late 80s. But if you pitch it today, you'll get $200 billion. So it's great. Okay, so the idea behind, so if you want to look for references for this kind of idea, the first line of work to think about is Dyna from Rich Sutton. And there's been a bunch of follow-ups, which we'll talk about, but look for Dyna. Okay, so the idea in this line of work is to say, we're not going to do test time planning, but instead we're going to use a model as a simulator and then learn a policy at training time, and we'll just deploy the policy through test time. Okay? And so we're going to say, our goal is going to be first to learn a model with maximum likelihood, just like we did before. Then we're going to do RL inside this model, right? RL inside this model is going to learn a policy, a Q function, etc. And then we're going to throw away the model and just deploy the policy, right? And so you can use whatever policy gradient or off policy method you want. But if you're going to run RL in the model, you can just use the policy as the optimal behavior and throw it away. And it'll be a lot faster at test time. It'll be slower at training time, faster at test time. Okay, so why is this not trivial? Like what could happen that is hard? Yeah.
The first model's already approximation.
Yeah, so your approximations keep compounding. You could have the hallucination problems we talked about earlier, right? And so the main thing to think about here is that if you're using the model as a data generator, so one way of thinking about how to do this is to say, you're going to learn some models, you're going to generate some data, and then you use it for off-policy RL. Let's say you're going to use it to train your Q functions and your policies with active critic. Right? So if you're going to use your model as a data generator, you need to be careful not to let the errors keep compounding or to like put in hallucinated things, because any hallucinated data here will show up right here. And hallucinations in the Q will show up in the pi, right? So RL is just a game of like managing approximations. Okay, so if you do this kind of thing, the main thing to be careful about is that if you take rollouts that are too long horizon, they tend to like hallucinate a lot, just like we've talked about. And so if you just treat the simulator like, if you just treat the model like a simulator and just run RL on it, it's not going to tend to do very well because the rollouts will get really long and deviate. And so this kind of thing doesn't do well when you're doing Dyna. Instead, if you do this kind of thing, it tends to do a lot better, right? So you say, start from real data, and then take short horizon rollouts, and then add that to your replay buffer for off policy error. And so I'm going to do Q learning or actor critic on synthetic data, right? Data I'm going to generate from my model, but I'm going to start from real data, and I'm going to generate short horizon rollouts. And there's like, depending on how wrong your model is and how susceptible it is to compounding error, the length of the rollouts will be different. But the point is that you want to start from real data and generate short rollouts, and those can be trusted, whereas like long rollouts will have lots of compounding error. So most instantiations of these methods like Dyna will start from real data, generate short rollouts, put that in the replay buffer, run off policy RL, run your policy in the world, collect more data and repeat, right? So the only thing you can really trust is real data and short steps from real data. And so there's an inherent trade-off between covering things and compounding error. Okay, so this is a nice paper. Should be in my slides, but it kind of like tries to mathematically quantify this trade-off. Okay, so the overall procedure for this kind of method, which let's call them Dyna-style methods, is to say we're going to collect some real-world data. We're going to use this real-world data to learn a model. This model is learned with maximum likelihood. You're then going to generate this data with short rollouts, right? Short rollouts branching off of real data. We're going to throw this data in the replay buffer for off policy RL. You're going to optimize a critic and an actor, Q and pi. You're going to use that pi to go collect data in the real world, and you're going to update your model. You're going to generate more data. You're going to update your policy. Right? So it's kind of like, you can think of it as it's doing like SAC or actor critic methods, but it has an extra synthetic data generation step. Right? So basically this is SAC, and you have this extra step of generating synthetic data. Right? So you can almost think of it as glorified data augmentation. It's data augmentation which respects the dynamics of the world. But it makes a huge difference in sample efficiency, and so that's what leads to it being helpful. And so here's an example from a few years ago, but the cool thing about this is that it like learns really fast in wall clock time. So one of the misleading things about model-based RL is that like the samples will be really small, but the training time will be so slow, or the inference time will be so slow that it's like actually takes 5 hours to learn, and they say it learns in like 3 minutes of real world data. But it's actually 5 hours of data, right? And we do this in our lab too. We do all sorts of fraud, but in general, you want to be careful about like not taking this at face value. Like typically you want to look for sample complexity, but also wall clock time. The model-based RL has really long wall clock time, and often it can only go really, really slow. It goes at like 1 hertz, so it goes really slow. Okay. All right, how are we feeling about model-based RL so far? Besides me telling you it's a fraud. Good? Yeah.
So how many samples do we like generate each before we do like place optimization?
I don't remember off the top of my head, but it's in the like tens of trajectories, not in the thousands of trajectories. So small. But look up that paper I mentioned. I think it has numbers. Okay. Here's the last 2 things we'll cover. The first is how do we scale this to images, right? Like we care about dealing with visual observations. In most cases, we care about camera observations. So the stuff we've talked about so far is largely applied to things like these Mojoko domains, etc. Or like, for instance, in this demo, it looks like it's from vision, but it's actually not from vision. You can see the robot is looking straight ahead. It's definitely not looking at the scene. Right? It's actually just trying to get the arm to a particular position. So these are not visual model-based RL methods. So the question is, what is it going to take for us to scale the domains where vision is a non-negotiable, right? Like something like robotics or egocentric navigation and things like that. And so the first question to ask is like, why is learning from images hard? Right? And so if you think about learning from images, this is from a few years ago. It's gotten a lot better since then, but action condition video prediction is still pretty hard. And so you'll see that like often it looks okay for a little bit, and then it'll start blurring and going through objects and hallucinating all types of stuff. right? And so long horizon predictions can be challenging. They start getting blurry. They start getting like unrealistic. And then even now, I would say like it looks pretty until you have to interact with the object and then you like hallucinate something crazy. The other thing is that with many of these video prediction models, especially with images, they're naturally partially observable, right? Like you don't see everything all the time, right? So you have to deal with partial observability. And so the key idea that folks have been using is that so far we've been thinking about a Markovian system where you're fully observed, you know the states, you're trying to predict the next states. Instead, they've been going to what you'd call latent space models, so things that are partially observed. So for those of you in my 478 classes, like Bayesian filtering, like the same thing. But you can see observations. It's a little hard to see, but these are observed. You can see actions, but you cannot see states, right? So it's like non-Markovian. You have to infer what the state is from a history of observations. Yeah. And you don't even know in this case, as opposed to Bayesian filtering, you typically know what the state space is. In this case, because it's like learning based, we don't even know what the state space is. Right? So the state space is a latent space. And so we're going to try and infer the latent space and learn its dynamics jointly. And so we're going to learn these latent space models that represent the dynamics in latent space, but also the encoder and the decoder from that latent space. Right? And so the key idea of learning from images that has been pretty successful is to not, like video prediction models try to go from image to image. Instead of going from image to image, we're going to go from image to latent space, plan in latent space, or do prediction in latent space, and then come back down to image space or to some decision-making space. So the question is, how do we actually learn such a model? Like, what does it mean to infer latent dynamics? We're not going to go that much into detail here, but the premise of many latent space models is to try to learn a bunch of different things together. Right, so we're going to try and first learn an encoder. And the encoder is trying to encode a history of observations into a latent space, let's call it ST. Right? Now, given an encoder that's going to give me ST, I'm going to learn a latent transition model. The latent transition model is going to say, given ST and AT, what is ST plus 1? Okay. And then you're going to have a decoder. And a decoder says, given some ST, can I go and predict OT, right? So you can kind of think of it as like, sorry. You can kind of think of it as like in a variational encoder, variational autoencoder, you go from XT to Z back to XT hat, right? In a latent space model, you go from OT to ST, ST to ST plus 1 hat, given AT, and then you go back down to OT plus 1 hat, right? So the grounding signal is the observations. You can't predict nonsense, right? But you're trying to predict, like here, this is just for one time step. You can think of this as a variational autoencoder for two time steps. Right? Yeah.
You like check your health of your latent space, or like what's the characteristics of latent space that's like conditioned well?
That's a good question. I don't think it's perfectly understood. So there's a line of work that tries to say, for instance, these kinds of papers, what they're trying to do is they minimize the divergence between a posterior and a prior. So when you say a posterior, it is saying like, what is the P of ST plus 1 given OT plus 1 and ST? That's a posterior. So you're getting information from the future, and you're trying to make that close to ST plus 1 given ST and AT. So they often make these similar, and that prevents degeneracy. But your question is about health of the latency. Often you check like, is it degenerate? So you plot like a variance in the latent space. Sometimes you look for like latent spaces that are good for planning. And so then you try to see like, are gradients well-defined in your latent space, or is our model simple in your latent space? So there's like a line of work that tries to learn models that are linear in your latent space. And so, yeah, I wouldn't say there's a canonical definition for it. So I think neither for any representation learning nor for latent models, it's kind of the same problem. We don't know what a good representation space is besides the downstream object. But yeah, it's a great question. Okay, so you're often going to learn an encoder, which takes me from OT to ST, a latent dynamics model that takes me from ST to ST plus one, and then a decoder that takes me from OT to OT plus one. And the idea is that I'm going to lift from OT to ST. I'm going to do a bunch of prediction in ST space, never come back down to OT. And then finally, I'm going to come back down to OT to ground everything. Right? But if I'm going to be in OT space, or if I'm going to be in, in the latent space ST, I need to make decisions in the latent space ST, which means that I don't have rewards anymore. So I have to train a reward model, right? So typically these latent space models lift me from OT to ST, but you also have a reward model that goes from ST to reward, right? So if I want to not come back down to observation space, then I need to have something that tells me what is the reward for a latent. So it could also be like a good latent space is something that makes reward predictable. So I'm going to have a latent space. I'm going to have a predictor, RT given ST, right? And then I'm going to make decisions by, let's say, if I want to do random shooting, I'm going to lift from OT to ST. I'm going to run a bunch of trajectories in my latent space. I'm going to evaluate the rewards for all of those, and I'm going to choose the best action, and I'm going to play that action. I'm going to repeat. Okay? So typically with these kinds of models where you're doing reconstruction is this thing where you're like reconstructing observations from states, reconstructing pixels. You are going to like use them as a training objective, but at inference time, you're not going to do reconstruction, right? So at training time, you're going to combine these different objectives. You're going to combine the objective of reconstruction. Right? So this is reconstruction. This is reward prediction. This is latent prediction. You're going to combine those objectives to train the model. And then at inference time, you're going to throw away reconstruction. You're just going to run steps in your latent dynamics model and pick the best actions. Okay. So the most canonical reference in this line of work is this idea called Dreamer. There's Dreamer V1, 2, 3, 4. So check out those lines of work. They give you lots of nice tricks on how to train these models. But essentially, as I said, you're going to encode, you're going to plan in the latent space, you're going to decode into rewards, you're going to pick the thing that has the best rewards, you're going to play those actions. Right? So the nice thing here is that you're avoiding predicting images at planning time. Like a video prediction model has to keep generating images, right? If you look at the prediction models we had back here, every time I have to make decisions, I have to generate a bunch of images. The nice thing about latent space models is I don't have to generate images at test time. I just have to use them as grounding signal at training time. And it should scale a lot better than image prediction. Right? So most methods that roboticists use for model-based RL are latent space models, not video prediction models. Not always, but many. And this has, at least so far, shown longer horizon prediction because I don't have to reconstruct. So here's a cool example from, I think, Dreamer V3, where they like learned a bunch of Minecraft skills from scratch using model-based RL, including mining diamonds and so on. But all of this is coming from like a hallucinated model of the world. That's the nice thing about Minecraft as a testing domain is that it's like quite partially observable. It's egocentric vision. And so the model has to infer its state from a long history of past things. They've also applied this to some robot tasks. And so the nice thing here is that you can get training from images in less than 1 hour for a bunch of different robotics tasks. Pick and place. They have this like interesting looking sphere thing, quadrupeds walking and so on. Right, but compared to off-policy RL, tends to be a bit faster. Okay, so a natural question that comes up in these kinds of methods is, okay, I told you I'm going to do reconstruction, but like, what if reconstruction is not perfect, right? So what are examples where reconstruction might not be great? When is not great to reconstruct the scene? Not a lot of extra information. Good point. Other thoughts? In robotics, often you'll have your camera placed in a way where your arm dominates the whole scene. But if you care about like decision making, you often care about the objects in the world, right? And so reconstruction typically rewards things that occupy the most pixels. And so you don't always want to reward things that occupy the most pixels. You want to capture the information that you need for decision. Right. So in these cases, there's a few different ways to do it. But the cons here is that this is a problem that's often canonical in exploration called the noisy TV problem. You have a noisy TV, and it's like playing a bunch of random stuff, but it occupies a huge amount of your scene. You're just going to waste a lot of your prediction power on the noisy TV, though it's irrelevant for decisioning. And if you have large objects, they tend to dominate your reconstruction objective. Okay, so we don't want to do reconstruction. How do we avoid reconstruction? Like, how do we do model-based RL while avoiding reconstruction? Latent space model-based RL, but we don't want to reconstruct pixels. How do we do it? Thoughts? We reward success. But I'm trying to learn a model of how the world works. So what should I predict?
Instead of having the ones for the construction, it could predict if the task will be successful.
Okay, yeah. So you can predict things like rewards and values. That's one way of doing it. What are other ways of doing it? How should we think about what to predict? The basic question I'm asking is, what should model-based RL algorithms predict? What should be, do we need to predict everything in the world? Or how do we predict task-relevant entities?
I guess if the thought is that you're trying to make a latent space that's like the most representative of like what you care about, then you just care about your latent space transitions being really good. So if you have a really good encoder, then all that would really matter is your transition to like the next latent space.
That's right. That's the idea behind JEPA and a lot of these methods. Basically, they're trying to do reconstruction-free latent space modeling. And so the tricky part, though, is if I don't have a decoder, if I have like OT going to ST, ST going to ST plus 1, and OT plus 1 going to ST plus 1, no decoder. There's like a trivial encoding, which is just send everything to a constant, right? And so often the like challenge in JEPA and so on, and they do this like exponential moving average, is that they're trying to avoid the degenerate solution. And so the tricky part is, how do I get this thing to be the trivially predictive answer is just map everything to constant. And so that's the tricky part. Okay, so a few ways that we've thought about doing this is, there's a paper called TDMPC 2, where you do what Harini was saying, which is predict rewards and values in the future, right? And the other way, which Yanda and Jacob and some others worked on, was to predict things that are semantically relevant, right? So if you're in a scene and you want to like, let's say like push certain blocks around, I don't need to predict the pixels. I just need to predict whether the block was pushed, whether I got closer to the block, predict the semantics of the word. So pretty open area of research, but I think something I want to like seed everyone to think about is just like, it's not super clear what should be predicted in model-based RL, but it's almost certainly not pixels, in my opinion. Yeah.
Train an encoder using some self-surprising.
Yeah. So there's a bunch of papers that do that. The tricky part is like, how do you know that's as Zeb was saying, like, well, how do you know that's a good latent space for decision making? Because you might have redundant information, you might have things that are organized in a way that's not very predictable. But yeah, that's totally reasonable way. That's the way that many of the like successful models do it now. Yeah. Good question. Yeah. So with these kinds of models, you're predicting specific things. And so your models are becoming task specific. And so the whole benefit we had with model-based RL is supposed to be reusable. And in this case, we're becoming task specific. So I mean, the simplest way I've seen of doing it is just make it multitask. So train it over enough tasks, and it kind of like represents something shared. The other way of doing it is there's a cool line of work on like predicting things that are controllable rather than things that are task relevant. Predict things that are controllable. So it's like if there's a pedestrian walking in the background, nothing you can do can change their action. So like discard things that are unpredictable. So then it's like task relevant, task agnostic, but like still discarding some information. Cool. All right. So the last bit we're going to cover is this idea called MCTS, Monte Carlo tree search. Right. So far we've discussed mostly continuous search methods, right? And so let's consider in this case discrete action spaces. So things like chess and Go and shogi and whatever, right? Like Atari games. Discrete action spaces, the state space can be continuous. But when you have something that's discrete, let's say you had like A choices at every step. You have a search tree that blows up, right? Like your search tree blows up, you can't represent your whole search tree in memory. And so the idea of Monte Carlo tree search is that like, let's focus computation on the areas that are more promising and not have to build a complete tree. And so you're going to use a combination of tree search and function approximation to deal with really, really large trees, right? So for instance, chess or Go is like an extremely large tree. You can't represent the whole tree. So you're going to use some combination of function approximation to represent things past your search horizon and tree search to do efficient search in that discrete space, right? So Monte Carlo tree search, you can think of as a model-based RL method. So you can apply it on known models. So AlphaGo, for instance, used Monte Carlo tree search on a known model, like the chessboard was known, right? And then you extend it to something like mu0, which applies it to a learned model, right? So they kind of show the same method is usable both on learned models and unknown models. The big idea here is that you can't actually simulate the whole tree. You can't actually represent the whole tree or search the whole tree. So how do you approximate it, right? And as the name suggests, you're going to do it with Monte Carlo approximation. So any Monte Carlo tree search method typically has 4 subcomponents. It represents a tree in memory. And for each tree element, it's going to represent a Q value, right? A Q value being Q S comma A, right? At any state, it's saying like, what are the different action options you have and how good are they? The data structure you're going to maintain is what the states are, how they're connected to each other. That's your model, right? And then you're going to represent a Q value, which is telling you what action you should take. But you're going to have 4 steps. And the first is selecting. You're going to select a path down your tree. Then you're going to expand one level in your tree. And then you're going to simulate a possible future beyond the search horizon that you're capping yourself at. And then you're going to propagate the result of your simulation back through the tree, right? So Monte Carlo tree search kind of proceeds by building a tree through selection, expansion, simulation, and backpropagation. And so you can kind of think of it as like you will have a tree capped out at some depth, right? But you're going to keep building that tree by first selecting a path through the tree, getting to some frontier node, expanding that frontier node, simulating a longer term future from that frontier node, seeing how good that was, and then propagating that value back up the choices that you made. Okay, so let's go through each of these one by one. The selection step is basically trying to say if I have a Q value, I want to choose things that are maximizing that Q value, right? So like, let's say I was at the top of this tree. I'm going to choose things that are maximizing this Q value. But I don't want to just choose the argmax because I won't explore the tree. And so I'm going to add in an element of optimism, which says that I'm going to pick things that haven't been picked very much before, right? So there's an idea from multi-armed bandits. Basically, it's optimism in the face of uncertainty. So if I haven't gone down a tree path much before, let me have some optimism to go down it sometimes. Okay? And it's easier to do here because things are countable. Okay, so in general, we're going to have the selection step essentially choose the argmax under the queue plus a bonus term, where the bonus term is inversely proportional to how often an SA tuple has been chosen. So if I have something that's been chosen a lot, I'm not going to give it a bonus. If I've not been choosing it much, that means I haven't even given the Q function a chance to get right. And so I'm going to reward it more. So you do that to like draw paths down your selection step. Once you do that, then you have the expansion step. There's not much to the expansion step. You just take one action from your frontier node that you stop at, right? You typically set the Q equal to 0 and equal to 0, and then it's updated through backpropagation. You just grow the tree by one node. This is the part that makes it Monte Carlo, which is to say that once you've expanded a node, you need to update its value beyond the depth of the tree that you've looked through. And for that, you're going to use function approximation. So you're going to say that, let me run my policy through the world. Let me see how good it was, right? And then I'm going to like approximate that through a Monte Carlo estimate. So I'm going to run, let's say, multiple rollouts here. I'm going to take a Monte Carlo estimate like we did in policy gradient, right? And then I'm going to propagate that value backwards. I'm going to simulate things forward. And so over here, I'm not going to maintain a tree beyond this. I'm just going to roll things forward. Okay. And so initially, you're going to start by running a random policy forward. And just to get like, how good is a random policy from a particular state? So in this case, the state would be something like a position in your chessboard or something. But eventually, you'll start replacing it with your current policy, your current optimal policy pi. And then finally, you're going to do back propagation, which is once you've got a Monte Carlo estimate, you know what V is here. And so just like we've done before, you can propagate V backwards for one-step backups. So once you know V here, you can propagate Q here and Q here and Q here. And so that's all that Monte Carlo tree search is. And they found that is super duper effective. And so perhaps most well-known demonstration of this is in mu0. So you start with AlphaGo, AlphaZero, and getting to mu0. Mu0 is with a learned model. AlphaZero is with a known model. Right? And you can see that it does significantly better than human performance in some games, which is kind of cool. And like the expansion of the tree is kind of shown on the top. Okay, so that's model-based RL. I think we finished 10 minutes early, but let's kind of recap what we did, right? So we started from random shooting plus NPC, simple, scalable, doesn't work that well in high dimensional spaces. We then added an MPPI, focus your search process. We said you could still hallucinate, so we added some uncertainty penalties. Said it's going to be too slow, so we amortized it into training time. We then said, okay, we want to scale the images. We're going to use latent space models. And finally, we said for discrete spaces, we can use Monte Carlo trees. Yeah. Okay, so as Harini was just asking, we said the benefits were transfer, efficiency, and simplicity. But if you're going to do transfer, but you're learning models that are specific to certain tasks, you lose the benefits of transfer. And so I think the interesting questions to think about here are like, how do I retain the benefits of transfer while being simple, efficient, and capturing only the things that matter? In general, model-based RL algorithms learn really quickly, but they often plateau at levels below model-free RL algorithms. So if you're trying to get some really hard tasks to work in simulation, I would never use model-based RL. I would use an algorithm that looks more like PPO, tends to work better. Okay, so maybe another thing that I think is interesting to think about is what is the difference between a model and a Q function? So if you think about a model is off policy, as is a Q function. Both you can train on any data. Both of them model something about the future, right? A model models a one-step state. Q function models the cumulative future, but both of them model things about the future. And they're both very different from policy gradient, right? So if you think about like a Q function, you're going from S, you're taking the cumulative future, and that's your Q function. Taking a model, you take S and A, it gives you S prime. Both of them are causal, they're forward. Whereas a policy is saying you're at S, you want some good outcome in the future. And so you try to predict the A that gets you there. And so you're kind of anti-causal. You're saying like, given this is the outcome I want in the future, what is the action I should take now? So policy gradient is quite anti-causal, whereas Q function and models are causal. Go forward. But there's some differences, right? So the first difference is that models are one step and Q functions are cumulative. Models model state, Q functions model reward, or cumulative reward. And models are not dependent on policies, right? So you're saying I'm going to evaluate S prime given SA. And Q functions are modeling Q for a certain policy pi, right? So I'm saying like this is the Q function when I play a policy pi, but it doesn't work for a different policy pi, right? And so models can evaluate any policy, whereas Q functions it's hard to evaluate any policy. Right? So they're related, but not quite the same. And so like the advantages of Q functions are you're only modeling what is needed for decision making. Like, do I need to model step by step? Probably not. But they're less transferable, whereas models are more transferable, but are modeling way more than is needed. So if you're interested, there's a nice line of work on successor features that tries to connect Q functions and models. So it lets you get the transfer benefits of models with Q functions. This is a way to generalize Q functions to many rewards to many policies. Cool. And I think that's it for model-based stuff. All right, I'll see you all on Monday. Thanks.